Hello and welcome to the second half of Lecture 21. In this part of the lecture notes and in these videos, we're going to get on to discussing the consequences of special relativity. In other words, we're actually going to make calculations using the theories of special relativity because as you've noticed so far, we've just been discussing the idea and the theory. All right, so our two objectives are to learn how relativity predicts that moving clocks run slow and how experimental evidence confirms this. And we also want to learn how the length of an object changes due to the object's motion. Okay, so that's right there, those two objectives encapsulate the idea that time and space, length, right, size, are relative. They're all depending on how fast you're going. These effects are not noticeable unless you're going an appreciable fraction of the speed of light. Okay, so one thing we're going to be doing a lot with special relativity is making these calculations that all end up having the same form. And so we can save ourselves a lot of time and make our calculations a lot easier if we recognize the similarity between the formulas and kind of that similar coefficient. And that coefficient is called the Lorentz factor, okay? And what it simply is it's represented by gamma. That's the letter that's commonly used and also used by your textbook. And it's simply equal to 1 over the square root of 1 minus the velocity you're traveling at divided by the speed of light squared. Okay? So for example, if you're traveling at 99% the speed of light, then this part right here, the v squared over c squared, would just become 0.99 squared. Okay? And then the idea of the Lorentz factor is that it becomes larger as v approaches c. So it becomes larger as v approaches c. Okay, so the closer you get to the speed of light, the bigger that Lorentz factor gets. And there's no limit to how big it can get. Okay? And that's going to be good when we look at the formulas because then we can kind of see a clear trend. You can be like, oh, well, look, this is proportional to that factor. So that means that this value is going to get bigger and bigger as velocity gets closer and closer to the ultimate speed limit, the speed of light. Okay? Now, there's a couple of terms that we're going to have to be really, really careful about, and that's proper time and proper length. And the first one I want to define for you here is proper time. Okay? And actually, let me change over one thing real fast. There we are. So, proper time, which is represented by t with a subscript of 0. So the subscript there implies proper because it's like the original time, like t naught, okay? And that is the time between two events measured in the frame where the two events occur at the same location, okay? So, for example, if I had a clock that worked by dropping a ball every minute, then if I'm in the same frame of reference as that ball drop clock, then the clock doesn't move relative to me, and so then measuring the time between ball drops would be in the proper time between ball drops would be measured by me if I'm sitting in the same room with this clock. Okay? Because then the clock isn't moving. All the ball drops, those are the two events or series of events, they all occur at the same location. Okay, because the clock is just sitting there in my room, right? But what if my room then is moving at 99% the speed of light? Well, someone that is maybe at rest on a planet nearby, as my room zooms past them, okay, if it was like a glass elevator they could see in, thought experiment, then they would measure a different time between the ball drops than me. But the proper time will be measured by me because the clock is at rest relative to me. Okay, so this is the time between events as measured in the frame where The events occur at the exact same location. Okay, so that would be the proper time between events. So you'll see that we have to always ask ourselves that. Who's measuring the proper time in a given problem? Okay? Okay, so now the first of the big consequences, and that is time dilation. Okay? So let's think about where time dilation comes from. All right? Well, it tells us that time measured, so we'll say that it's the idea that measured time in any other frame will be longer than the proper time. Okay? So if events are occurring at rest in my frame, any other frame moving relative to me will measure a shorter time between events. So it's the idea that measured time in any reference frame other than the one that measured proper time will be longer. So in other words, t, that's measured time in any reference frame other than the reference frame that measured the proper time, will always be larger than t naught. So t is always larger than t naught. That's the absolute inequality here. Okay. Now sometimes that effect is so small that we cannot measure it or don't notice it. But when we're moving at significant fractions of the speed of light, then we definitely do notice it and can measure it. Okay? So, kind of thinking about why that is, consider the thought experiment shown above. Okay? And I have a couple of these, so this would be this one here. So the idea is that Mavis here is sitting at rest relative to a little device that sends a wave and records the wave coming back. Okay? So for her, the two events would be the emission, so the source of the wave, and then the reception, which would be the receiving of the wave. Okay? Because again, this little cylinder here is both a sensor and like a laser. And the way it works, obviously, is it shoots a beam up. That beam bounces off the roof because there's a mirror attached to the roof. And then when the beam comes back down, it can record it. Okay? So very simple device. And it will measure a time interval between emitting the wave and receiving it, the reflection of the wave back, of delta t naught. That's the proper time, isn't it? Because this device and the two events that happen, sending the signal, receiving the reflected signal back, they occur at the exact same location relative to Mavis. So she measures the proper time. So the two events occur at the same location in her reference frame. Okay. Meanwhile, Stanley observes the same light pulse following a diagonal path. Of course, right? Because what's happening now is that this thought experiment train is moving at high speed to the right at some velocity u. Again, remember we use u to represent the velocity of the reference frame. And so it's moving very quickly to the right, so quickly that it's already moved a significant distance, so this distance right here, by the time the light gets to the roof. Okay? Now that means that it has to be moving at a significant fraction of the speed of light. Otherwise, this horizontal distance would be tiny, infinitesimal, by the time the light got to the ceiling, right? In most cases, in most trains. Okay? But here the train is so fast that the light clearly takes a diagonal path. Okay? And so Stanley will then measure a longer time interval for the time it takes the light to go to the top, reflect off the top, and come back down to that same sensor. Still, both events are happening, There's no disagreement about the events. The signal was sent and received. But the light pulse travels a longer distance. And remember, it's a light pulse. So that means that the pulse of light here in the vacuum of the train, or near vacuum of the train, is at c. Okay, so v is c. And both Mavis and Stanley agree that the light is traveling at that velocity. So the only way for that to be true, the only way for them to both agree that the speed of light is universal, which of course has to be based on Einstein's second postulate, first and second postulate, that the laws of physics are universal, regardless of your reference frame. So if they agree that the speed of light was c, then the only way for that to be true is for more time to have passed in Stanley's reference frame. So he might say that it took 2 milliseconds for the light to go from the sensor, we'll say how about 2 nanoseconds, from the sensor back, or it was sent from the sensor to get back to the sensor. Mavis says 1 nanosecond, okay? All right, so there you go. That's a thought experiment that shows that time is relative and that the proper time will always be the smaller time. Okay, let's now talk about proper length. Similar idea, and I want you to think of proper length and proper time as being two sides of the same coin. So in other words, you can solve a problem by considering relativistic time, or you can solve that same problem by considering relativistic length in most cases. So it's really kind of up to you. They're not separate phenomenons. They're just two ways of looking at the same thing. Okay, so first of all, we need to define it. It's super important here. Okay, so proper length is represented by L naught. Okay, like so. Use the kind of the lowercase cursive L. Okay, and is the length of an object as measured in the frame where the object is at rest. Okay, that seems totally reasonable, right? So length, that sounds proper. Okay, so length of an object measured by, or say measured in the frame of reference. Getting used to that term, frame of reference? Okay, hopefully. Where the object is at rest. Okay, so let's define length contraction and then run through the thought experiment with Mavis and Stanley, but just focusing on a different thing. Okay, so the idea then is that the proper length will always be greater than the improper length. Okay, so the idea is that the length measured in any other reference frame will be shorter than the proper length. Any other reference frame. And of course, when I say any other reference frame, I mean any other reference frame than the reference frame where the proper length was measured. But I'm going to shorten the sentence to say length measured in any other reference frame will be less than the proper length. Okay, so it's the opposite effect in a sense, right? Because it's the idea is that all the lengths are going to be shorter than the proper length, whereas all the times other than the proper time were longer. Okay, but those two ideas come from the same place. So the idea then is simply that L would be less. Now let me use lowercase l. L would be less than L naught. Okay, let's make sure we can run through the thought experiment to consider why. Okay. So we're going to again have a beam of light, but this time, instead of measuring the time it takes for the beam of light to do something, we're going to measure how far it goes. Okay? And notice this thought experiment is based on the light traveling kind of parallel to the motion rather than perpendicular. It's just well suited to that. So that's kind of interesting, isn't it? So here again, we have Mavis sitting in her relativistically fast transparent train, right? Our thought experiment train. The ruler is stationary in Mavis's frame of reference, S prime, that's the way we always denote, the moving frame of reference. And the light pulse travels a distance L naught, so that's the proper length, from the light source to the mirror. Okay? So that's the distance that Mavis would measure that the light travels from the source to the mirror. Okay? We're not interested in events here because there's no time. We're just interested in how far the light travels. Okay? And she can definitely lay down a ruler between her sensor and the mirror and physically measure it. Okay? Okay, so meanwhile, Stanley, okay, standing there, watching the train go by. I guess it's this relativistic train is not stopping at the station. The ruler moves at a speed u, okay, again, because that's the velocity of the reference frame, shown here. Okay, reference frame S prime, okay. Stanley's in S because he's in the rest reference frame. Okay, and that's, of course, relative to the reference frame S, Stanley's frame. The light pulse travels the distance L, the length of the ruler measured in S, okay, plus an additional distance U delta T, okay, from the light source to the mirror. Okay, so then what length will Stanley see, right? So let's make sure I'm saying what I want to here. So I'm going to pause for a second. Yeah. So we should have the length contraction. It should appear shorter. Right, and we do see that it appears shorter. Okay. Because it does look like it's so the distance it travels appears to be longer here. But why is that? So light travels a distance L, the length of the millimeter, plus an additional distance U delta T 1. This is how much time it took for the light to go from the source to the mirror. But again, we're not talking about D. D is not what we're comparing. So D is the distance that, so essentially D is the distance that Stanley sees that the light traveled. But the length is then going to be that distance subtracted by U delta T. So what Stanley will see is a shortened ruler. Okay? So the length, it will appear to basically have covered a shorter distance. The ruler will be contracted, it will be shortened from the reference of Stanley. Okay? Okay. So let's run through our formulas here. So first of all, we have the speed of light. I included this version. This is basically the most accurate version we have of the speed of light. Just for, I know it has a lot of significant figures, but that's for times where we want to consider values that maybe are very close to the speed of light, or just to get a very accurate calculation if we're trying to look for a very, very subtle effect. Okay? But for most of the time, we're just going to use 3.00 because you can see to 3 sig figs, it would round to 3.0 times 10 to the 8 meters per second. So that's fine to 3 significant figures. Okay, so now the rest of the formulas. Okay, I want to go through these formulas and then we'll finish this video. Okay, so again, we've got this will allow me to say a bit more about the proper time, proper length and length contraction, because I don't think I did it justice just a minute ago with the figure, but we'll have an opportunity in just a minute to circle back around to the equation. Okay, so let's go through these. I'll label everything that needs to be labeled. Okay, so first of all, delta T naught is the proper time. That's I think that's what the light reflecting off the ceiling with Mavis. Okay, so here we have proper time. Okay, and this is kind of a derivation. Obviously, you're not going to see D and C show up most of the time, but I just want to show where it comes from. Okay, so then we have the idea that delta T is the time measured in any other reference frame. So this is time, we'll say this is the time measured in the rest reference frame. So time measured in rest reference frame, just like with Stanley and Mavis. Okay, so in that case, it was 2L over C. So it was twice the distance divided by the speed, and the distance to the ceiling just back down. L was the hypotenuse of the triangle, if you recall. Okay, so it's longer than D, and it was longer than D based on this right here. So the idea is that there's a right triangle right here, and the bottom of that right triangle is 1/2 U delta T. So this one right here is 1/2 U delta T, and then the height of that triangle is still D. So therefore L is just going to be, using the Pythagorean theorem, the square root of 1/2 U delta T squared plus D squared. Okay, so that's what we see here. Okay, and then we can just work through this. And all I do here is I just rewrite D as based on the proper time. So now I've expressed D in terms of the proper time, which is good because now we have an equation that's going to relate measured time in the rest reference frame to the proper time in the moving reference frame. Because again, the proper time is measured in the moving reference frame. Okay, in this case, if we were measuring events that were happening at rest, then the rest reference frame would measure the proper time. Okay, so that's what you gotta pay attention to. So then when we clean this up, when we factor out the delta t and then naught, and then solve for delta t, it becomes this. It's just a matter of algebra. And then we can see that we have our Lorentz factor. Okay, we have exactly the gamma is the Lorentz factor. Just a way to kind of save time when we're writing this. And it's just 1 over the square root of 1 minus u squared over c squared. Okay, and the u is just the speed of the reference frame. Okay, that equals gamma. Oops. There. Okay, so that's a wonderful way to clean it up. And indeed, we can see that delta t is always going to be longer than delta t naught, right? You see, because I mean, if I plug in a very large u here, right? So if I plug in u, equals even just 80% the speed of light, then this would become 0.8 squared. 1 minus 0.8 squared is going to be a small fraction, okay? Then I take the square root of that, so then I'm dividing 1 by a small number, which means my gamma is going to be greater than 1, right? So gamma is always greater than 1. And then since gamma is always greater than 1, then multiplying by gamma means that delta t is always larger than delta t naught. Okay? So I'll leave that up, that it's always greater than 1, because it's a good thing to remember. Okay, so now let's think about the length contraction. Okay, so that's this derivation here. Okay, so same thing. We'll start with the proper time, and then we're relating the proper time to the proper length. Okay, so this is the proper length. That's just the length measured in the reference frame where the object is at rest. In the Mavis-Stanley example, that would be Mavis's reference frame because the ruler is at rest relative to her. The ruler is definitely moving relative to Stanley. Okay, and the length of the ruler, right? So it's just the time that the light would take to travel along the ruler would just be twice its length, and then divided by c. And again, that's because it's got to go and then come back. So it's got to hit the mirror and then bounce back. Okay, so here's the distance that Stanley measured. That's the one that's bigger, and that's why I paused a second ago. But that's not the new length. That's just the distance that Stanley sees the light travel. So Stanley would see the light travel some distance L, okay, because he would see it travel along the ruler, but then he'd see the ruler move as well, right? So think about that, because you'd be able to tell that the ruler was moving as the light was moving, and so then the end of the ruler is a moving target. So then that end of the ruler would have moved forward. He'd still see the physical ruler, but he'd see that the end of the ruler move as the light kind of is going along, trying to catch up with the end of the ruler. Okay, so then he would see the distance the light travels as the length of the ruler plus an extra distance that was covered because the moving target, because the end of the ruler is moving ahead. Okay, and then that would have to be equal to the speed of light times the time it took for the light to travel that distance. Okay, so then that means that the time that he measured would be the length of the ruler over c minus u. And all I've done there is just solve for delta t. All I've done is just divide both sides, basically just solve for delta t from this expression. Okay, let me make sure. Yep. So I'm just going to, divide both sides by c. And then, okay. Okay, so essentially, I guess what I'm saying here, in this line here, I'm saying that the time it takes the light to travel in Stanley's reference frame would be the length of the ruler that he measures, and then over c minus u, because it depends. It's the faster that the train is going, it's going to take more and more time to catch up with the end of the ruler, because again, the end of the ruler is trying to outrace the light, right? It never will. But what if the ruler is moving at 99% the speed of light? Well, it'll take a lot longer then for the light to travel to the end. So that's why it's L over c minus u. So that's just by the idea that the ruler is racing ahead. And then this delta t2, that represents the time for the light to bounce back, because that would be faster, wouldn't it? Right? Because then the light then is able to, now the sensor that's going to receive the signal that's bouncing off the mirror at the end of the ruler, right? Because the mirror's right here, and then the light comes back. That's going to take less time as measured by Stanley, because then Stanley will see the sensor catching up to the light. So then it has less time to travel. Okay? So then we can say that from Stanley's perspective, the total time is going to be the sum of those two times. So it's going to be delta t1 plus delta t2. Okay, so and then when you do the algebra, we get this expression here. So delta t, that's the time measured by Stanley, is just delta t1 plus delta t2. Okay, so that's all I've done. Okay, and sort of these two steps, right? These two ways of thinking about it. It's just kind of confirming this idea about, what is the distance, why there's an extra distance measured, what times Stanley measures, and so on. Okay. And let's see then. So what we want to do then is we want to, add the two times together, which will then just give us 2L, and then factor out the C from the expression. That's why there's a 1 here, because they both had a C. And then since we added them together, when we do a common denominator, we end up with minus u squared over c squared. Okay? And then that right there is just going to be, really, that is just gamma delta t naught, right? That's we've expressed it in a way where, because you think about 2L over c is going to be related to delta t naught, right? And then because we've just divided by the Lorentz factor, okay, or in fact multiplied by the Lorentz factor, okay. So we can then point that out, that this is actually just another way of writing gamma delta t naught, right? So that's basically the same result we got up there, but we're getting it with length this time, right? Well, like I said, they are two sides of the same coin. But then to finally circle around and relate it back to length, what we want to then do is then take that delta t and basically put it into an expression for length, or just solve for the relationship between length and proper length. Okay, because we've got, essentially then we could then say that this has to then be equal to gamma times 2 L naught over c. So then if I solve for L, right, which is right here, if I solve for that in terms of L naught, then I get this expression right here. So then we see then that the length measured by Stanley is the proper length measured by Mavis, where the ruler is at rest, divided by gamma. And since gamma is always greater than 1, that means that the relativistic length will always be shorter than the proper length. Thus, L is always going to be less than L naught. Okay? So certainly the length contraction is a bit harder to get there. The time is really simple because we were able to draw that triangle and it was very, very simple to explain. But hopefully that all makes sense, and ultimately you are going to be using the equations, not having to rederive them. I just wanted you to have some background on the topics. Okay? And so the two equations that you really are going to be using, I'll put a box around them because there's a lot of derivation here that could be distracting, but it's going to be these two here. It's going to be your time dilation formula, okay, that's this one, and your length contraction formula. And think about those terms, right? Time dilation, because time is always longer in any reference frame other than where the proper time is measured. So dilation means growing, or it's bigger. I think your pupils get dilated, they grow. So time dilation, and then length contraction, because length is always less than the proper length. Okay, good. Well, thank you for watching, and please tune in for the second